This is lecture 1G, the final lecture in preparation for test 1. First topic today is going to be polyprotic acids. These are acids that have more than one ionizable hydrogen ion in their formula. HCl would not be an example of a polyprotic acid. There's only one hydrogen in the formula of HCl that when it undergoes a Bronsted acid-base reaction, usually with water, it would donate that hydrogen ion to the water. So this is not a polyprotic acid. If we want to be specific, we can call it a monoprotic acid. Acetic acid, HC2H3O2, has 4 hydrogens in its formula, but when acetic acid reacts with water, there's only one hydrogen that it actually donates to the water molecule. That's due to the structure of the acetic acid molecule. It's an organic acid, and it has the carboxyl group in its formula, the CO2H unit. You can see at the right side. And the carbon, which is double bonded to an O and single bonded to another O, has an H bonded to that O, and that's the one hydrogen that if it interacts with a water molecule gets donated. So this is also not a polyprotic acid. It would be considered a monoprotic acid as well. H2SO4, however, is a polyprotic acid. This has 2 hydrogens in its formula that can be donated to a pair of water molecules when it interacts with water in a Bronsted-Lowry acid-base reaction. So we would say, yes, this is a polyprotic acid, and if we want to be more specific, we can call it a diprotic acid because it has 2 hydrogen ions or 2 protons that it can donate when acting as a Bronsted acid. H3PO4 is also a polyprotic acid. It has 3 hydrogens in its formula that could be donated to 3 separate water molecules. And so we could be more specific with this one. We could call it a triprotic acid. So we're going to be looking at polyprotic acids today. And a polyprotic acid will actually have an equilibrium constant, an acid ionization constant value for each of its ionizable hydrogen ions. If we take carbonic acid as an example, this is definitely a diprotic acid, 2 hydrogens in its formula. When the carbonic acid molecule interacts with a water molecule, the water molecule will pull 1 hydrogen off of the carbonic acid molecule, creating a hydronium ion, and then the polyatomic ion bicarbonate. This reaction will reach an equilibrium. Carbonic acid being a weak acid, this will be an equilibrium system, and there will be an equilibrium constant expression we can write for this. The equilibrium constant will equal the concentration of the hydronium ions multiplied by the concentration of the bicarbonate ions divided by the concentration of carbonic acid. The equilibrium constant for this first ionization of the polyprotic acid H2CO3 is called the Ka1, the one indicating the first hydrogen is being removed. And there's an experimentally determined numerical value for the Ka1 for carbonic acid. It's actually found on handout 3. Its value is 4.3 times 10 to the minus 7th. Now, once the bicarbonate ion has been formed, the HCO3 minus, that ion could now interact with another water molecule, and a similar reaction could take place. The bicarbonate ion, by bumping into a water molecule, can donate its hydrogen to the water molecule, creating another hydronium, and now finally the carbonate ion. This reaction will reach an equilibrium because the bicarbonate ion is also a weak acid. And let me point something out. The formula for the bicarbonate ion, HCO3-, has 3 O's and 1 H. It appears to have 2 more O's and H's in its formula, so one might think mistakenly that's a strong acid. But the rule for an O's to H's ratio, being 2 or more O's and H's to be a strong acid, only applies to neutral acid molecules. It does not apply to polyatomic ions, such as HCO3-, which is an intermediate form of the polyprotic acid H2CO3. So don't apply the ratio of O's to H's for any polyatomic ion that can still act as an acid. So this is going to be a weak acid, and the equilibrium constant for this reaction is going to be called the Ka2 because this is now going to be the equilibrium constant for the ionization of the second hydrogen in the carbonic acid. The products are the hydronium ion and the carbonate ion, and the reactant is the bicarbonate ion. And this Ka2 has a numerical value, and from handout 3, it's 5.6 times 10 to the minus 11th. So something I want you to notice here, because this is always true for polyprotic acids. Successive hydrogens always have smaller Ka values. So the Ka1 is 4 times 10 to the minus 7th. The Ka2 is 5 times 10 to the minus 11th. 4 times 10 to the minus 7th is a bigger number. So the first Ka for a polyprotic acid will always be bigger than the second, and if there's more, the second will be bigger than the third. This means as the constants get smaller, the hydrogens are harder to remove. So it's always easiest to remove the first hydrogen ion from a polyprotic acid. It's harder to remove the second hydrogen, and if there's another, it'd be hardest to remove the third. So therefore, in terms of acid strength between H2CO3 and HCO3-, we would say H2CO3 is a stronger acid because it releases its hydrogen more easily, and then HCO3- must be a weaker acid because it holds onto its hydrogen more strongly. Now, what I'd like you to be able to do is I would like you to be able to predict the pH and the concentration of all the species that exist in the solution of a polyprotic acid, and we're going to do a carbonic acid solution as an example. We're going to find the concentrations of each species in a 0.10 molar H2CO3 solution. When you're dealing with polyprotic acids, and because polyprotic acids have multiple ionizations, we have to deal with the ionizations one at a time. So the first thing we're going to do to figure out the concentrations of all the species in this solution is to imagine the carbonic acid undergoing a reaction with one water, which would be the reaction for its first ionization. So I'm going to take the carbonic acid molecule, react it with a single water molecule. It'll transfer a hydrogen to create a hydronium ion and the bicarbonate ion. Now, if we want to calculate the concentrations of all the species that are in this solution at equilibrium after this reaction has occurred, we're going to write an ice table. And so the initial molarities here for the carbonic acid, it was originally said to be 0.10 molar, and we'll assume that none of the carbonic acid has reacted yet, so there won't be any products from that. Because there are no products, the forward reaction has to be spontaneous, so the coefficient in the balanced equation, 1x of the carbonic acid molecules will ionize, and you'll form x molarity of the hydronium ions and x molarity of the bicarbonate ions. Adding the columns, once you've reached equilibrium, you'll have 0.10 minus x molar of carbonic acid, x molar of hydronium, and x molar of bicarbonate. These three equilibrium molarities are related to each other through the equilibrium constant, which is the ratio of the molarity of the products to the molarity of the reactants. And because this is the reaction for the first ionization of carbonic acid, the equilibrium constant is called the Ka1. So the Ka1 will be hydroniums times bicarbonate over carbonic acid. If we know the Ka1 and we know the equilibrium values for all three species, then we can actually now solve this for x. I'm going to first ignore the x in the denominator. I'm going to redo the denominator as only 0.10, and I can do that because the equilibrium constant is so small, we know x will probably be small compared to 0.10. And if I do that, I can solve for x, and x comes out to two significant figures, 2.1 times 10 to the minus 4th. And if you test the 5% rule, this is definitely less than 5%. So we can assume this is the correct value for x. So what have we learned so far? At this point, at equilibrium, the carbonic acid concentration is going to be 0.10 minus x. So that's going to be 0.10 minus 0.000207. And a good example of significant figures determination for subtraction problems, the 0.10 is only accurate 2 places past the decimal point, where the 0.00021 is accurate 5 places past the decimal point. So when you subtract them, you have to round your answer back to only 2 places past the decimal point. And so this answer essentially just rounds to 0.10. So it's almost as if none of the carbonic acid ionized, but actually a small amount did, but you would have to report it as 0.10 molar. The hydronium ion concentration at this point is just going to equal x. So to 2 significant figures, 0.00021 molar. And the bicarbonate ion concentration at this point is also x, 0.00021 molar. Now, these are not the final answers to the question because these would just be the molarities if the polyprotic acid only underwent one ionization. But it undergoes a second ionization, so now we're going to have to determine how maybe these molarities change because of the second ionization. You can see they probably have to because if we have the bicarbonate ion and it's going to start to ionize, its concentration is going to go down. So to continue the problem, we're now going to write the second ionization for carbonic acid, which is going to be starting with the bicarbonate ion. And the bicarbonate ion will react with another water molecule, take a hydrogen from the bicarbonate to form a hydronium, and will produce the carbonate ion. This reaction will reach equilibrium. So to determine the molarities of all the substances in this equation at equilibrium, we're going to do an ice table for this one as well. Now, let's think back. What's the concentration of the bicarbonate ions to start here? It's not 0.10. That was the molarity of carbonic acid. The bicarbonate ion concentration is what we got from the equilibrium line in our previous ice table. That's the 0.00021, or with a guard digit, 0.000207. So we only have this small molarity of bicarbonate ions in the solution. And most of the problems we've done so far, when we go to the right side of the equation, we write 0 and 0. But in this case, that's not true, because after the first ionization, we also created some hydronium ions. Its molarity is also 0.000207. There are no carbonate ions. This one has to be 0. So the second stage of a polyprotic acid calculation, where you're trying to find the concentrations of all the species, this second ionization is always going to have equal amounts of the intermediate form of the acid, the bicarbonate in this case, and the hydroniums. Because there's a 0 on the right side of the equation, the forward reaction has to be spontaneous, so I'm going to lose some of the bicarbonate using its coefficient in the balanced equation. I'm going to go -1, and I'm going to use y now, not to confuse it with the x as I did for the first equilibrium calculation. And if y of the bicarbonate ions react away, I'm going to form y of the hydronium ions, and then y of the carbonate ions. At equilibrium, we're going to have 0.000207 minus y, 0.000207 plus y, and y, because we love you. These three equilibrium concentrations are related to the equilibrium constant for the second ionization, which is the Ka2. And the expression would be the concentration of hydroniums multiplied by the concentration of carbonate divided by the concentration of bicarbonate. If we know the Ka2 and we can plug in all the equilibrium values from our ice table, we can now solve this for y. And we're going to use the approximation technique as well as this, otherwise we're going to have to solve a quadratic. With the constant being so small, that means any time a variable is added or subtracted from a number that's probably going to be a lot bigger, it's probably going to be insignificant. So in the denominator, my minus y, I'm going to get rid of that because I'm going to assume y is going to be really small compared to 0.000207. And if that's true, well, it has to be true in the numerator as well. If I'm going to add a really small y value to 0.000207, it's probably insignificant also. So I'm going to ignore each of these. And now the calculation actually becomes really simple, because on the right side of the equation, I have 0.000207 divided by 0.000207. They cancel out, and therefore y just equals 5.6 times 10 to the minus 11th. So now that we've solved for y, let's go back and think about every single species that exists in this particular solution. We first have the carbonic acid molecules. They were not affected by this equilibrium, so what was their molarity from the first equilibrium? 0.10. The hydronium concentrations are affected by this equilibrium. From the first equilibrium, they were 0.000207, but then we had to add y to that, so we're going to add 0.000000000056 to that, and it turns out in terms of significant figures that 5.6 times 10 to the minus 11th is so small it actually doesn't even affect the number. So the concentration of hydronium ions essentially stay 0.00021. For the carbonate ions, or for the bicarbonate ions now, if we look on our ice table above, it's 0.000207 minus y. So we're going to calculate that by subtracting 5.6 times 10 to the minus 11th. But in this particular case, once again, it's so small, doesn't affect our original value. So the bicarbonate concentration is 0.00021 molar. Finally, the carbonate ion concentrations just equal y, and so that means they're going to wind up being 5.6 times 10 to the minus 11th molar. So these are going to be the concentrations of all the species in this polyprotic acid solution once both ionizations have occurred and have reached equilibrium. Now, something else about a polyprotic acid is I want to talk about the reaction that involves the complete ionization of the polyprotic acid. When carbonic acid undergoes ionization with water, it's a two-step process. Now, the carbonic acid will react with one water molecule first. That water molecule will pull off a hydrogen to create a hydronium ion and a bicarbonate ion. The equilibrium constant for this reaction is called the Ka1, and its numerical value is 4.3 times 10 to the minus 7th. The bicarbonate ion now can interact with another water molecule. If it does, that water molecule pulls the hydrogen off of the bicarbonate ion, forming a hydronium ion and a carbonate ion, and the equilibrium constant for this second ionization is called the Ka2, and its numerical value was 5.6 times 10 to the minus 11th. If you were to add these two reactions together, you would get the complete ionization of carbonic acid. And if you do that, you're going to wind up getting H2CO3 plus 2 H2Os yield 2 H3O positives plus a carbonate ion. And if you've noticed, the bicarbonates don't appear there because there's one bicarbonate on the left, bottom reaction, and one bicarbonate on the right in the top reaction. They cancel out. So we would call this the complete ionization for carbonic acid. And if you want to write the equilibrium constant expression for this, it's going to wind up equaling an equilibrium constant whose name is going to be the Ka1, 2. We call it the Ka12. So what's the numerical value for the Ka12? I'm going to sort of show you how you can analyze what this should be. I'm going to write out the Ka1 expression for our first reaction. That's the molarity of hydroniums multiplied by the molarity of bicarbonate divided by the molarity of carbonic acid. That's our Ka1 expression. Now I'm going to write out the Ka2 expression. That's going to be the molarity of hydroniums multiplied by the molarity of carbonates divided by the molarity of bicarbonates, like this. If you were to multiply these two equilibrium constant expressions together and then simplify them, and these can be simplified because the bicarbonate in the first expression cancels out with the bicarbonate in the second expression, you're going to wind up getting this. The concentration of hydronium ions squared multiplied by the concentration of carbonate divided by the concentration of carbonic acid. And if you see what that is the equilibrium constant expression for the complete ionization of carbonic acid. So the Ka12 expression is related to the Ka1 and Ka2 expressions. You have to multiply them to make that. So if you multiply the Ka1 expression by the Ka2 expression to get the Ka12, that means that if you multiply the numerical value of Ka1 by the numerical value of Ka2, that will equal the Ka12. And so if we actually do that, we can get the numerical value of the Ka12, which is the complete ionization for carbonic acid. That comes out 2.4 times 10 to the minus 17th. This is an important concept. We talked earlier this unit about related equilibrium constants. And if you take a chemical reaction and let's say you double all the coefficients, the new equilibrium constant will be the old equilibrium constant raised to the power of 2. If you reverse a reaction, its new equilibrium constant will be the reciprocal of the original equilibrium constant. We use those quite a bit. Here's a third thing I want you to know. If you add two different equilibrium reactions together to make an overall equilibrium reaction, the equilibrium constant for the overall equilibrium reaction will be the product of the equilibrium constants for the two reactions you added. So the last topic we're going to discuss in our unit on acids and bases is going to be pHs of salt solutions. It makes sense that if you dissolve an acid in water, like acetic acid or hydrochloric acid, you're going to get an acidic solution pH less than 7. If you dissolve a base in water, like ammonia or sodium hydroxide, you're going to get a basic solution that's going to be above 7. Water would just have a pH of 7. Water's neutral. But what if you dissolve salt in water? Well, sometimes salts will actually make solutions acidic or basic, and it's going to be up to you to figure out whether it does make a solution acidic or basic, and then we're going to finish off by trying to determine what pH the solution would be for a particular salt. The reason that salts can make acidic or basic solutions is that the ions that make up salts are actually conjugate acids and conjugate bases. If I take the salt X plus and Y minus, and that could be like sodium chloride, right? NaCl, it's made up of a positive ion and a negative ion. Well, positive ions are always conjugate acids. They're conjugate acids of the base, in this case, XOH. So if, let's say, X was potassium, that's a potassium ion. The potassium ion is the conjugate acid of potassium hydroxide. The negative ion in all ionic compounds are actually conjugate bases. They're conjugate bases of the acid, in this case, HY. So if Cl was the chloride ion, Cl minus is the conjugate base of HCl. So therefore, salts are actually made up of acids and bases themselves. And let's think about this. Let's say we have a cation that's in a salt, and the cation is NH4 positive. All cations are acids. They're technically conjugate acids. What would be NH4? What would NH4 positive be the conjugate acid of? According to what we have up in yellow above, all we have to do is stick a hydroxide on it, and that's going to be the base it comes from. So NH4 positive would be the conjugate acid of NH4OH. Now, NH4OH actually doesn't exist. If you get into the lab room and we're going to be doing experiments and you need to get a solution of ammonia dissolved in water, sometimes the bottles will actually say NH4OH on them, but that's actually incorrect. This compound doesn't exist. NH4OH is really just a water solution of ammonia. So if you actually apply the actual definition of what an acid does, an acid loses a hydrogen ion, then if NH4 is a conjugate acid, when it loses its hydrogen ion, it becomes its base, which would be NH3. So you can always predict what base it comes from just by either adding a hydroxide to its formula or taking off a hydrogen, because that's what acids do. They lose hydrogens. If you know that NH3 is a weak base, what can you conclude about the conjugate acid? We talked about this before. If you have a weak base, its conjugate has to be weak as well, and that's going to be an important thing for us to be able to predict as we go through trying to predict whether salts are making acidic or basic solutions. What if we have a sodium ion in our salt? Well, sodium is an acid. It's the conjugate acid of what base? Stick a hydroxide in its formula, NaOH. What kind of base is NaOH? That's a strong base, and so that means Na plus must be a non-acid. Now, how does this Na actually the conjugate acid of NaOH? Well, that's because a sodium ion, when it dissolves in water, can actually have a water molecule attached to it. So if it has a water molecule attached to it, you can use the Bronsted-Lowry definition of what an acid is. If this substance now loses a single hydrogen ion, what's left over? NaOH. So that's how cations can actually be thought of as conjugate acids. Just attach a water molecule to them. When they lose their one of their hydrogen ions, they now become a base. But as I said, if sodium hydroxide is considered a strong base, then the relationship between a base and its conjugate acid is if the base is strong, the conjugate acid has to be non, which means it really doesn't react with water. Let's look at some examples of the conjugate bases that could exist in ionic compounds. Let's say we have a nitrate ion. If the nitrate ion is in a compound, that's the conjugate base of some acid. So what acid is it the conjugate base of? This is a little bit easier to predict. You just stick a hydrogen on it. It's the conjugate base of nitric acid. What kind of acid is nitric acid? That's a strong acid. So what kind of base is the nitrate ion? It's a non-base. Strong acids have non-conjugate bases. What if we have the nitrite ion as the ion in our salt? What would be the conjugate acid of that? Just stick a hydrogen on it. Sticking a hydrogen on that would make nitrous acid. What kind of acid is nitrous acid? That's a weak acid, so therefore the nitrite ion must be a weak base. So we're trying to illustrate a point that we had made earlier in this particular chapter. Anything that's strong will always have a non-conjugate. If you have a strong base, the conjugate acid is non. If you have a strong acid, the conjugate base is going to be non. And then anything that's weak will have a weak conjugate. So a weak base has a weak conjugate acid. A weak acid has a weak conjugate base. If you can do that, then you can predict whether salts will produce acidic or basic solutions, and we're going to now try some examples. So predicting if ions in salts will act as either acids or bases, first we need to have a salt. Let's start with this one, lithium phosphate. So the way you predict if this is going to create an acidic or basic solution is just by identifying the two ions that exist in the salt. Salt, just another name for an ionic compound. And although there's 3 of them in the formula, we just have to know that lithium ions are the positive ion in the compound, and then phosphate is the negative ion. So I'm not really worried that there's 3 of them. I just want to identify what the ions are. So this salt is composed of lithium ions and phosphate ions. So here's what we have to do. We have to analyze them one at a time. You have to ask yourself, because this is a conjugate acid, what base did it come from? So how do you figure out the base it came from? You add a hydroxide to it. So if you add a hydroxide, or we could actually go by the strictly the definition of Bronsted-Lowry acids, you lose their hydrogens, you could remove a hydrogen. But the easier way in most cases is just add a hydroxide, you would get LiOH. What kind of base, you have to ask yourself, is LiOH? That's an alkali metal hydroxide. And all the alkali metal hydroxides from the first column in the periodic table are strong bases. So if this is a strong base, you will therefore conclude that the lithium ion must be a non-acid. That's the point you want to get to. If it's a non-acid, that means it doesn't react with water at all. It has no effect on the pH. So the lithium ion does nothing. Let's go to the anion. This is going to be a conjugate base. So you have to go, what base does it come from? And you figure that out by adding a hydrogen ion to it. So if you add a hydrogen ion to it, you get HPO4 2-. So what kind of acid is this? Well, if you know H3PO4 is a weak acid because it only has one more O than H in its neutral form, and then successive hydrogens are weaker and weaker, this definitely has to be a weak acid. So if this is a weak acid, what can you conclude about the phosphate ion? It's going to be a weak base. So this salt is made up of a non-acid, the lithium ion, and a weak base, the phosphate ion. So the lithium ion does nothing, but the phosphate ion acts as a weak base. It's going to actually react with water a little bit as a base and make the solution basic. So therefore, this salt will have a pH on the basic side of 7. It'll be greater than 7. The reason is that the phosphate is acting as a base. It reacts with water and it pulls a hydrogen off of a water molecule. So when you dissolve lithium phosphate in water, the lithium ions will do nothing, but the phosphate ion will bump into a water molecule, and every once in a while, because it's weak, it'll pull a hydrogen off, forming HPO4 2-, and you'll get a few hydroxide ions in the solution. That makes the solution basic. Anytime an ion in a dissolved salt reacts with water to form either a basic or acidic solution, could be either one, we call this process hydrolysis. So this is the reaction of a dissolved ion with water. So questions you may see are, they'll be giving you a salt. They'll say, do you predict whether it's going to have a pH greater than 7, less than 7, or equal to 7? And if the pH is greater or less than 7, write the hydrolysis reaction. That means you have to identify what ion, the cation or the anion, is reacting with water as an acid or base, and then write that acid-base reaction. Let's try again. Let's take the salt ammonium chloride. You have to identify what ions are going to be in the solution. These two ions will separate from each other, and you'll have ammonium ions and chloride ions, and now we have to analyze them one at a time. The cations are always conjugate acids, so you have to ask yourself, ammonium is the conjugate acid of what base? So how do you get the base? You either add a hydroxide to it, or you do the definition of what an acid does, you remove a hydrogen from it. So you either add a hydroxide, you get ammonium hydroxide, or you remove a hydrogen and then you get ammonia, which is really what exists. So ammonium is the conjugate acid of ammonia. Now, ammonia is a base. What kind of base is ammonia? It's a common base, but it's not a strong one. This is a weak base. So if ammonia is a weak base, what can you conclude about the ammonium ion? It has to be a weak acid. So the ammonium ion is going to be making this solution slightly acidic. Let's see what the chloride ion does. Chloride is a conjugate base of some acid. How do you figure out what acid it comes from? You just add a hydrogen ion to it. If you add a hydrogen ion, you get HCl. What kind of acid is HCl? That's a strong acid. So if HCl is a strong acid, what can you conclude about the chloride ion? Strong acids have non-conjugate bases. Okay, so therefore the chloride ion doesn't react with water at all, but in this salt, the ammonium ions are. They're going to react with water as an acid. They're going to make the solution acidic. The pH is going to be less than 7. What would be the hydrolysis reaction? It'd be the NH4 positive plus a water molecule, and then the NH4 acts as an acid, donating a hydrogen ion to create ammonia and the hydronium ion, which is what makes the solution acidic. Let's try one more. Let's take the salt potassium nitrate. To analyze whether this will make a solution acidic or basic, we need to determine what ions are floating around in the solution by this dissolved salt. And it's just from the name, potassium nitrate, there'll be potassium ions and nitrate ions. So let's analyze them again. So this is the sort of roundabout way you need to do it. Potassium ions are conjugate acids. They come from some base. How do you figure out what base it comes from? Well, it's a positive ion. You stick a hydroxide on it because hydroxides are negative. So when you stick the hydroxide ion on it, you get KOH. Once you've figured out what the base is that it came from, you have to go, is this strong or weak? And this is an alkali metal hydroxide. That means it's a strong base. So if KOH is a strong base, that means the potassium ion is a non-acid. I used to say, oh, that makes the K plus a bad acid, but I don't know, that didn't sound good. So I decided to call it a non-acid instead. So K plus is a non-acid. Let's go to the anion. These are always conjugate bases, and they're conjugate bases of some acid. How do you figure what acid? Well, these are negative ions. Stick a positive hydrogen on it, and then you'll know. Sticking a positive hydrogen on that, you get HNO3. HNO3 is a strong acid. It has 2 more O's and H's. So if that's a strong acid, what must be true about its conjugate base NO3 minus? It's a non-base. So when this salt dissolves in water, you have the potassium ions, which are non-acids. They don't react with water. You have nitrate ions, which are non-bases. They don't react with water. So this particular salt solution would actually maintain a pH of 7 because neither of its ions will undergo any reaction with water. So that's how you predict the relative pH of a salt solution. Now we want to see if we can calculate what the pH of a salt solution will be. This is usually the most missed question on exam 1. So if you want to see if you can get this one right and not miss the 8 points on test 1 like many people do, then follow along here. We're going to see if we can find the pH of a 0.10 molar potassium acetate solution. So you got to do the analysis first, just like we did before. Is one of these ions going to react with water? So this salt contains potassium acetate. So potassium is a conjugate acid. It comes from what base? Potassium hydroxide. That's a strong base, so the potassium ion is a non-acid. It's not going to react with water. Acetate is a conjugate base. It comes from what acid? Acetic acid. And acetic acid is a weak acid, so the acetate ion must be a weak conjugate base. So analyzing both ions in the formula, because potassium ions come from potassium hydroxide, which is a strong base, the potassium ion is a non-acid. The acetate ion comes from acetic acid, which is a weak acid, so the acetate ion must be a weak base. So the acetate ion is the only one that's going to react with water, and it's going to react with water as a base, and so this solution is going to be basic. Now, we know that pH is going to be greater than 7. How do we calculate the exact pH? Well, we're going to need to have the Kb for the acetate ion, which is acting as a base. The Kb for acetate, however, is not found on handout 3, but something that is on handout 3 is the Ka for its conjugate acid, acetic acid. Its value is 1.8 times 10 to the minus 5th. So how do we get the Kb value for acetate if it's not listed on the table? Well, watch this. Let me write the Ka reaction for acetic acid. That's going to be acetic acid plus water is in equilibrium with hydronium ions plus acetate ions. Now, let me write the Kb reaction for the acetate ion. What would that be? Acetate plus water. It's not the reverse reaction, okay? It's acetate plus water. Ka and Kb reactions are always an acid or base reacting with water. So if the acetate ion reacts with water, it pulls a hydrogen off of the water molecule to create acetic acid and a hydroxide ion. I want to add these two reactions together. If I do, the acetic acid molecules are going to cancel out, the acetate ions are going to cancel out, and the sum of these two reactions is going to be two water molecules yielding a hydronium ion plus a hydroxide ion. Do you know the equilibrium constant for that reaction? It's called the Kw. So if the Ka for acetic acid reaction is added to the Kb reaction for acetate, and they add up to make the Kw, how are the Ka and the Kb related to the Kw? They must multiply to make the Kw. So therefore, if you ever know the Ka of an acid, you can calculate the Kb of its conjugate base, and that's what we're going to wind up doing here. So using this expression, I'm going to solve for the Kb of the acetate ion. That's going to equal the Kw for water, which is 1.00 times 10 to the minus 14th, divided by the Ka of acetic acid, which is 1.8 times 10 to the minus 5th. And when you divide these, we will get the Kb of the acetate ion, which comes out to two significant figures, 5.6 times 10 to the minus 10th, but with a guard digit 5.56 times 10 to the minus 10th. So that's the equilibrium constant for the acetate ion acting as a base with water. So now we have to write out that hydrolysis reaction for the acetate ion acting as a base. We know the equilibrium constant for it, so we're going to do an ice table for that reaction. So here we go. The acetate ion reacts with water as a base, gains a hydrogen ion to form acetic acid, and you have a hydroxide ion. Let's do an ice table for that. Our compound of potassium acetate was 0.10 molar. By inspection, there's one potassium in the formula, so the molarity of the potassium ions would be 1 multiplied by 0.10. There's one acetate in the formula, so the molarity of the acetate ions are going to be 1 times 0.10. That's how I know this number. Now, before the acetate reacts with water, nobody put any acetic acid in there, and there weren't any hydroxides in there. So now we have a system where the forward reaction has to be spontaneous, so some small unknown amount of the acetate will react away to form acetic acid molecules and hydroxide ions. Adding up the columns, the equilibrium molarity of the acetate ion will be 0.10 minus X, and the concentrations of the two products will be X and X. The equilibrium molarities are always related to the equilibrium constant of the given reaction, and because you're writing a reaction of acetate acting as a base, the equilibrium constant for this reaction is called a Kb. So the Kb for acetate will be the products over the reactants. And we've just determined what the Kb was. It was 5.56 times 10 to the minus 10th. That's going to wind up equaling products over reactants, x squared over 0.10 minus x. I'm going to ignore the x in the denominator, and then I can solve this for x. X turns out to be 7.5 times 10 to the minus 6th. If you test the 5% rule, it's way under 5%. So we can assume this x is correct. And in this problem, what did x stand for? It stood for the concentration of hydroxide ions. So if we've determined the hydroxide concentration at this solution at equilibrium, we can calculate the pOH. So the pOH is going to be the negative log of the hydroxide ion molarity. The molarity is a two significant figure number, so when we get our logarithmic answer for the pOH, it'll have to be expressed two places past the decimal point. That comes out 5.13. Don't accidentally stop there and say, oh, the pH is 5.13. That's an acidic pH. That would make no sense. You've calculated the pOH here. So we get the pH itself by going 14 minus the pOH. So 14 minus 5.13 will give us a theoretical pH of this potassium acetate solution of 8.87. Let's try one more example of this. Let's say we have a 0.25 molar ammonium chloride solution, and we want to predict the pH of this. Now, you're going to have to analyze what ion is going to react with water. Ammonium is a conjugate acid. What base does it come from? If you pull a hydrogen off of ammonium, you get ammonia. And ammonia is a weak base, so that means the ammonium ion must be a weak acid. Chloride, the negative ion in all ionic compounds, are conjugate bases. They come from acids. What acid does chloride come from? It comes from HCl. What kind of acid is HCl? That's a strong acid. So the chloride ion must be a non-base. So therefore, the ion that's going to react with water, the ion that's going to undergo hydrolysis, is the ammonium ion, and it's going to make the solution acidic because it's an acid. So you would need to look up the Ka for ammonium. If it wasn't given in handout 3, you could look up the Kb for ammonia and then calculate the Ka by going Ka times Kb equals Kw. But we actually have in handout 3, the Ka for ammonium, it's actually listed. It was 5.6 times 10 to the minus 10th. If you want to take a minute on your own and try to calculate what the pH of the salt solution will be, we'll let you do that, and then we'll go through it here. So the hydrolysis reaction you would need to do would be the ammonium ion acting as a weak acid with water, giving up its hydrogen ion to water, forming the hydronium ion, why the solution will be acidic, and you'll produce ammonia. This reaction will reach equilibrium, and so we're going to start with the initial molarity of the ammonium ion. They told us 0.25 molar ammonium chloride, and the formula of that compound, NH4Cl, has only one ammonium in it, so the molarity of the ammonium ions will be 1 multiplied by 0.25 molar. And before it undergoes any hydrolysis with water, there wouldn't be any hydroniums, there wouldn't be any ammonia molecules. Some of the ammonium has to react away, unknown amount X. You'll form 1x of hydroniums, 1x of ammonia, and adding the columns, you'll actually have the equilibrium molarities of all three. These equilibrium molarities are related to the equilibrium constant for this reaction, which is called the Ka of ammonium, and that Ka will equal the expression ammonium ion, hydronium concentration times ammonia concentration divided by ammonium ion concentration. The Ka was looked up, 5.6 times 10 to the minus 10th, and that'll equal x squared over 0.25 minus x. Because the Ka is so small, 10 to the minus 10th, we'll ignore the x in the denominator, and that makes it an easy algebraic equation to solve. X turns out to be 1.2 times 10 to the minus 5th molar, and if you test for a 5% rule, this is less than 5%, so we can accept this as the value for x. Because x stood for the hydronium ion concentration, the pH will be just the negative log of x, and the negative log of this turns out to be 4.93, so we would predict that a 0.25 molar ammonium chloride solution would have a pH of 4.93. So that concludes all the material for exam 1. Let me give you a list of things that you want to make sure you understand completely before we take our test. We started by talking about the concept of equilibrium. You need to understand what that is and what it means. And when a system reaches equilibrium, it turns out the ratio of the concentrations of products to concentrations of reactants always equals the same number. We call that number that it equals the equilibrium constant. I'll expect you to be able to write an equilibrium constant expression for any chemical reaction. Now, there's a relationship between the balanced equation and the equilibrium constant. Coefficients in the balanced equation become the exponents. I'll expect you to know that. And then if you have a solid or liquid, it does not appear in the equilibrium constant expression, so you would not include those. If you take a chemical reaction and you multiply the entire chemical reaction by some factor like 3, that means the new equilibrium constant must be raised to the 3rd power. If you reverse a reaction, you take the reciprocal of the equilibrium constant, and if you add two reactions together, we've learned that the product reaction is going to be the product of the equilibrium constants that you added together. We learned that the equilibrium constant can be expressed as the ratio of molarities or the ratio of pressures. So for gaseous reactions, you may have an equilibrium constant that's either a Kc or a Kp, and you should be able to convert between those. You'll need to know the relationship Kp equals Kc multiplied by RT to the delta N. If you calculate the ratio of products to reactants for a chemical reaction that's not at equilibrium, that ratio does not equal the equilibrium constant, but it equals a value that we call the reaction quotient, or Q, and that's important in trying to determine whether a system will be undergoing a spontaneous reaction in the forward direction or the reverse direction. And then we talk about Le Chatelier's principle. You should understand what that principle is. And then applications would be to determine the shift direction or the new equilibrium concentrations if a system at equilibrium is given a change in either the concentration or the pressure of one of the reactants or products, you change the volume of the container, or you change the temperature of the reaction. And finally, concerning Le Chatelier's principle, you should understand and predict the effects of a catalyst on a system at equilibrium. In terms of calculations, you'll need to be able to calculate equilibrium molarities from a Kc and initial data. This will be requiring an ice table to be written. You should be able to calculate the equilibrium constant from experimental data. Simply, if they just give you all the equilibrium molarities of the reactants and products, you should be able to get the Kc. But you should also be able to do it if they give you initial molarities and then one equilibrium molarity. By using an ice table on that last clue there, you'll be able to calculate the Kc. Or from initial molarities and percent dissociation. Once again, an ice table will be involved, and the percent dissociation will be a clue that you'll be needing before you can calculate the Kc. You'll need to be able to calculate equilibrium pressures from a Kp and initial data. And I'll expect you to be able to calculate the Kp if you're given all the equilibrium pressures or initial pressures and one equilibrium pressure. You'd solve that with an ice table on that clue there. Or initial pressures and percent dissociation, solve that with an ice table and then the percent dissociation clue. Or, which is quite common, initial pressures and then the equilibrium total pressure done with an ice table and then the equilibrium total pressure allowing you to calculate what X is in your problem. And then I would like you to be able to calculate initial molarities or pressures. If you're given a Kp or Kc and a clue, every once in a while a problem is not asking you for an equilibrium molarity or pressure, it's asking you for an initial molarity or pressure. I'd like you to be able to do that also. So that was all from the chapter on equilibrium. For our acid-base chapter, I would like you to know the definitions of Bronsted acids and Bronsted bases, and you should know what conjugate acids and conjugate bases are, and I would like you to know the relationship between their strengths. If you have an acid or base that's strong, you need to know the conjugate is non. If you have an acid or base that's weak, then the conjugate will be weak as well. We talked about how water molecules actually undergo a small amount of ionization on their own. That's the autoionization of water. And the equilibrium constant for that reaction for the autoionization of water is called the Kw. And I would like you to know its numerical value at 25 degrees Celsius, which is 1.00 times 10 to the minus 14th. We talked about the concepts of pH and pOH, so you should know what those are. You should know the relationship between them. pH plus pOH equals 14.000. And then we did some calculations where you had to figure out the pH of a strong acid or a strong base. These assume complete ionization or complete dissociation when you're calculating these. If you have a weak acids do not ionize completely. They reach an equilibrium, so they'll always have an equilibrium constant called the Ka. Weak bases do not react completely. They reach an equilibrium, and so weak bases have base dissociation constants called Kb's. And I would like you to be able to calculate the pHs of either weak acids or weak base solutions using their Ka and Kb's and writing ice tables for the calculation. Then I would like you to be able to determine the Ka or Kb from initial molarities and then some other clue, either given the pH of the equilibrium solution or the percent ionization of the equilibrium solution. Today we talked about polyprotic acids. You should know what those are, and you should be able to calculate concentrations of all the species that exist in polyprotic acid solutions. We'll see how you do that on your next homework assignment. Then we talked about the relationship between Ka of an acid and the Kb of its conjugate base, and that relationship is the Ka of an acid multiplied by the Kb of its conjugate base equals the Kw. I could have said this the other way around. I could have said the Kb of a base multiplied by the Ka of its conjugate acid also equals the Kw. And then we talked about predicting the pHs of salt solutions and then calculating the pHs of salt solutions, so you'll have those on your homework as well. We'll have completed experiments 1 to 5, so I would like you to know what we did on those experiments. There'll be questions on the test from those. The first one was on graphing. You should be able to make graphs yourself and then read graphs, slopes, be able to predict data points on that. 2 of the labs dealt with spectroscopy, so you need to be able to use spectroscopy data to be able to calculate things like equilibrium constants. For Le Chatelier's principle, I'll expect you to be able to write net ionic equations for the reaction that causes an equilibrium to shift. And experiment 5 is our first qualitative analysis lab, so I will ask you questions from that. So I would like you to specifically know the procedural steps and the results from that lab. And of course, you've done the reading for the 2 chapters. That should be it. We're done with the material for test 1.